Hello, today I want to record a video about global and local extrema points. It's very important in uh, model optimization process. So we can look at the graph and see there are global and local minima points, and basically global is the highest point in the entire function, and global minima is smallest point in the entire function. Local minimum and maximum are a local small peak between two valleys. So between two sides, it's the smallest or biggest uh, point in particular part of the graph. So basically, we have to find the tool that allows us to find such points in the graph, and that tool is derivative. It allows us to find the such points, dips, and peaks on the curve. Derivative, basically the formula conceptually is how our delta y, the relationship of delta y with delta x, how our y changes when our x changes. This is basically explanation of what is derivative. And it allows us to see if our function is increasing or decreasing at a particular point. Basically, if we have positive derivative, it means that our function is increasing the particular point. If it's negative, it means our function is decreasing a particular point. And if we have our derivative equals to zero, it means it's possibly extremum point. It's either maxima and minima points. That's it. If you'd like to calculate how we can find this derivative value, we can do this with first principle method, applying limit to delta x. That leads to zero. It's very small number. We can calculate in such a way that this is the global formula of finding derivative. It's our function plus delta x minus our function, and this whole we divide by delta x. So in such a way we can see our derivative value. Another name of derivative is slope in geometrical way of explaining things. So let our function to be x squared, and we can calculate it like this. By opening the brackets, we get this this way of writing the same, and x squared and minus x squared will be cancelled out, and we will have just double x multiplied by delta x plus delta x squared divided by delta x. So here we will divide both terms by delta x. We will write it like this. So now we divide both sides, and we will get double x plus delta x. So because delta x is a very small number, we can simply cancel it out, and our answer is derivative of x equals to delta x. So we just found by applying this principle, rather than rederive from this first principle every time, we can use table with standard derivatives of functions. It's not something that you, I think, really should memorize, but some of them you can memorize if you use them on your work. So basically, every of this function can be explained in step by step by rederiving them from first principles. Now we will talk about order, uh, second derivative. Basically, if we derived function, we've got particular function as a result. Now we can reapply again our derivative principle and get second derivative to be written like this. And why it is useful? Basically, second derivative can show us if our function concave down or concave up in a particular point. It's very important if we want not just to understand if this point is particular, if you want to know exactly if it is point local, if it is point minima or maxima, because first derivative won't tell us if this point is minima or maxima. It will tell us that this point is extremum, but not what kind of extremum is this point. So we can apply second derivative to get that information. So if you have a second derivative, the function is concave up, local minimum. Concave up means smile, and if our second derivative is negative, it means concave down. Our function is sad. So basically, how we can apply this knowledge in practice, there are two methods. When we found our first derivative equals to zero, all right, we found our critical point, or it might be either minima or maxima. So now we can apply one of the methods. Method one is sign change of our derivative function. If our derivative changes from negative to positive, uh, it means if the value of our derivative function is increasing, it means the function goes down then up minimum. Sorry, I will explain again. I might made mistake. If sign of the derivative changes from negative sign to positive sign, it means the function goes down initially, then goes up. So it goes down and then up. It means it's minimum point. Our function is smiling. If derivative changes from positive value to negative, it means function grows, and find the peak, and then goes down. It means that the point is maximum. Our function is sad. So, and second method is second derivative test. If we find the second derivative for the particular point, if that point is greater than zero, so it means the curve is smiling there. Smiling means minimum point. If our second derivative is negative at that point, means maximum, and the curve is frowning there. So the difference is that second derivative test is often faster. Instead of plugging different values into uh, points left and right between our extrema point, we can just just plug a value into that particular extreme point of the first derivative, and we will get our sign, and we will understand if this point is maxima or minima. So let's calculate example of finding extrema of function x cubed minus 6x squared minus 15x minus 15. So first we'll compute the first derivative. How we do that? Just by applying this formula rule by um, we have to place our power by multiply our variable to this power nx, and we have to subtract 1 from our power. It's basically simplest rule of finding derivative for simple functions. So we will get 3x squared minus 12x minus 15, and our last term will be cancelled out, because not cancelled out, it will, because it doesn't have any x on it. Means our function it doesn't affect change in our function, because it's a constant number. And we find critical points by solving this equation. We will have to place this function to be equal to 0. Such a way we will find two possible roots, solutions of this equation. And so we found possible 2 points, extrema points, that if we plug into our equation, we will get 0. So we will get 0. It means this particular point is extrema. And now we have to find a second derivative of this function, and it will be 6x minus 12. And now we plug our extrema points into second derivative function. First we plug 5, we will get 30 minus 12 equals 18. So 18 is bigger than 0. It means our function concave up, smiling. And our second extrema point, minus 1, we will plug it into second derivative function. We will get minus 6 minus 12, and it is minus 18. So below 0, and it is a local maximum. So our function is set in that point. So that this is the easiest way how we can find our maximum and minimum points on the by using second derivative method. All right, we found a way how we can find the extreme points, but we don't know how to define if this particular point is local or global extrema. And as I said in the beginning, global extrema would be absolute highest or lowest value across the entire domain, entire function. But not all the functions have global maximum. For example, x squared parabola function, it's constantly increasing, so we cannot find maximum point of such function. So we found local values only. So it was the first step, and we can continue. We can continue to work on it, and so far we worked with functions just with one single variable, independent variable that changes. But in our quality functional, the square error function we wrote down before depends on three parameters simultaneously. We have beta 1, 0, and beta 2. So how can we find extreme functions with multiple variables? So basically the same logics might be applied here. So basically if we have more than one variable, the logic is the same. And so, for example, if we have function z of x and y equals uh, x squared plus 3 multiplied by y squared. So This will be two partial derivatives. We will find how our function z changes when x changes. Separately, we find how our z function changes when our y changes. So this is the way how we can find partial derivatives for both of functions, for both of our variables, and we will get uh, partial derivative. First one will be double x, and second 6 multiplied by y. So uh, our critical point will be such a point that x and y are both equals to 0. So if you have more than one variable, we have to count both variables to find critical point. So our extrema point is 0 and 0. So basically we found two critical points, 0 and 0, and these points are external of our function, but we don't know yet if it is minima or maxima. So we apply second order condition, compute all second partial derivatives, and assemble them into basically here some advanced fancy mathematical stuff is happening. We found from double x and 6y, we found these two, and we see that in our partial derivative double x, we see how step, I think steeper our function is in that particular, if how strong it's, how strong concave up it is. I cannot explain in English, sorry. So if you see that 6 it's much stronger, and 2 it's softer, more shallow. Mhm. But both of them mean smiling function concave up. And there are also these two things we calculated, how changes uh, y for our partial derivative x, and how changes x for our partial derivative y, I guess. And I'm actually I don't understand this yet. We got this Hazen matrix with at the critical point 0 and 0. We got this matrix, and somehow this matrix tells us that this is local minimum. So our function is smiling at this point. I think maybe later I will understand how these Hazen matrices are working and what is Sylvester's criterion and how does it work. But I think for me it is enough right now just to understand that we have two second order derivatives, and they are both positive, so we don't have any negative of them. So it is enough for me right now to see that this function is convex concave up with minimum at 0 and 0. Whew, all right. This was a bit difficult. This derivative topic is a bit difficult for me, and I never tried myself to explain these things on English language also. So it might be, it wasn't the best explanation, definitely. But anyway, I think my understanding increased a bit with help of this recording of this video when I orally explain myself. I feel some more understanding coming to me. So thank you for watching this, and I will continue in the next video. We we are going in a way of understanding machine learning. It's not a simple question, simple challenge, but let's do it.